yeah, let us start recording. I'm recording here and I'm recording here. And let's go to the full screen. Okay, so we have finished our midterm exam, right? And so quite a few of you have already presented twice in the semester, and some of you haven't presented yet. So those who haven't presented yet, yeah, make sure try to finish everything in the second half. So we are now in week 8 already, right? We are kind of going towards the second half of the semester, and it's going to be, usually time goes very fast, right? Especially during the second half of the semester. You guys will have assignment and things like that. So yeah, just try to take note. Also, don't forget, we also have an assignment that is due on the very last day of the semester. So if you have time, you know, try to take a look and get it done early. Just clear it out of the way, right? And settle it, and then they will be good. If not, then the due date is the last day of the semester. So one thing to take note and keep in mind. And besides that, I guess we shall just continue on discussing the harmonic oscillator, right? Going to be more painful. Yeah, sort of, right? So if I think to me, I would equate, when you say pain, it just means new chapters and new topics. And yeah, in year 2, everyone is learning a lot of new topics. Year 1 is basically, I mentioned this before, right? High school topics, but in a more difficult problems to solve. But here we are learning some new methods for today as well, what we're doing here as well. So in the previous class, we have solved the harmonic oscillator using the ladder operator approach, right? The creation operator, annihilation operator, and then the number operator. Somehow, using that calculation, we can derive the wave function and energy levels of the harmonic oscillator. We're going to solve the harmonic oscillator again, but this time we will use what is called the analytic solution. Basically, the solution in calculus, right? So it's a more of a standard method, so less tricky and less fun, probably. Even the Griffiths textbook, they call the operator method. It's a bit more fun because it's like somehow like magic, the solution come out. But here we shall also see how the solution comes out. It's not, maybe not as magical, but maybe we can clearly see how the energy levels can still come out using a totally different method. Okay, so that's what we're going to do today. So let me remind you, what is the equation that we want to solve. We want to solve the time-independent equation for the harmonic oscillator. So the harmonic oscillator is described by the Hamiltonian, which is p squared over 2m, right? And then plus half m omega square x square. So this is the Hamiltonian acting on some state. And if I want to find the eigenstates of this harmonic oscillator Hamiltonian, it means that the Hamiltonian acting on this will give me back the state again, but with some value E. This E is going to be the energy. So I want to find what is this solution to this equation. So to do this, in order to solve this equation using the analytic solution, we go to the position representation. Right, so that means we are using x as our variable. So if using x as our variable, our harmonic oscillator equation is taking this form, right? Momentum is h bar over I, momentum squared, you got this, so this one is fine. I think you guys understand this already. And then this one is just half m omega squared. The operator x just changed to the variable x, and this is acting on the eigenfunction psi x, and then this gives me the energy E psi x. Okay, so I write the bracket here. It means that this thing can multiply inside, so it's the second derivative of psi times this thing times psi is equals to this. So we got a differential equation to solve. Okay, so what we're going to do is we're just going to solve this differential equation. This is an ordinary differential equation. So yes, we're going to spend the whole day today solving this equation. Okay, so let's get started. Last week, loss. Yeah, I totally understand if it's lost, because the operator method is a new thing that we are not used to, right? But here is a bit more down to earth. But let's solve this today. well, we have a bunch of constants everywhere. That's the troubles. That is why quantum mechanics sometimes is troublesome. So what we're going to do is we're going to simplify notation a bit. So we're going to let instead of using x, right, I'm going to do a change of variables. I'm going to express x in terms of m omega square root y, so that when there's an x square, right, I will just change this to h bar over m omega y square. So the derivatives, if I do this, right, so if I differentiate this twice, is the same as this thing upside down twice, so the square root disappear, and it's the same as differentiating y squared. This is just a changing of variables, right? You have done this since calculus 1. But if I express it in this form, what's going to happen to my equation? So the constant is h bar squared over 2m. The second derivative is m omega over h bar, second derivative y. And I got half m omega square. And then there's an x squared. So x squared means I substitute into y, it means m omega y square, and then times psi. So now psi is going to be expressed in terms of y now, and then I got e times psi. So notice that we purposely define it this way so that the m will cancel, and omega, 1 omega will cancel, this h bar will cancel here. So everybody has a factor of h bar omega. So I'm going to take it out, h bar omega. There's a factor of half for both as well, so I'm going to take the half outside also. And then take out, everything has been taken out already, so I got second derivative of y. And then this is just everything taken out, so it's just y squared psi e psi. Okay, so just tidy up a little bit. This one, like I said, right, when we write bracket out of the differentiation, it just means the psi dy square, and then this is y square psi. And then this thing I multiply to the other side, I got 2e over h bar omega psi. Okay, and this is also a bunch of constants divided by other constants. So let's just call this constant and just a single name lambda. So I'm just going to call this lambda, so that now instead of this messy equation, the differential equation that we want to solve actually looks like this, right? So it's a bit more simple, I guess. And let me rearrange this. So I want to make this the positive sign. So the psi dy square, right? Make it look more standardized. And then this one, bring this over. So I got y squared minus lambda. Both terms have psi, so I can factorize this out. Okay? So at the end of the day, what do I mean when we want to solve this? It just means that we want to solve this differential equation. So this is an ODE, and we want to solve this today. Okay, so in the same way I wrote in the previous class, right, our job, right, our quest, our mission for today is to solve this differential equation. And I'm going to call this equation 1, right? So this is going to be the main equation that we want to solve today. So I hope everyone follows so far, right? We did not do much yet. We haven't even started. I'm just changing variables so that I hide all the variables under y, so that it less messy. All right. So now we want to solve this. Okay. So more math. Yeah, the math is the language of physics. Unfortunately, we can't avoid it. Right. So now let's solve this. So I'm going to show you a few new methods that people usually tend to think about when we try to solve an equation that is very difficult to solve. So this equation looks very short, but how to get a solution? It's not like you can get a characteristic polynomial and things like that. Maybe you can, but the expression is going to be messy. So what we're going to do is first, we'll do this kind of like the physics way, is to first check the asymptotic behavior. So this is the kind of thing that people do quite often, whether in quantum mechanics or in relativity or things like that. Because in physics, right, something happened in this room, something very far away is not relevant to something happening here, right? So usually we check whether the asymptotic structure makes sense or not. Okay, So asymptotic behavior, let's see what happens when y is large. So if y is large, right? And let's say it's way bigger than this constant lambda, whatever this value is. If this is way very large, then the ODE becomes what? Well, if this is large, that means if this is way bigger than this, then this one is negligible. So my differential equation is asymptotic to, so this is a symbol to indicate it's not equal because I'm making an approximation. I am throwing away lambda. It's not 0, but it's just neglected. I'm just neglecting it. Okay, and it's approximately equals to this. And if my equation is this, then the solution is this one we know. If it's y squared, then the solution is some constants times e to the power of negative y squared over 2. Okay, so right now it's not very justified, right? You might feel lost by thinking that how come I suddenly do this, right? Yeah, well, let's just think of me as doing it for no apparent reason for now. Let's just roll along with it. Okay, this is the solution. If this is the equation, right? We are just asking what if. If this can become this, then the solution is going to be this. We can check whether what I'm saying is correct or not. So let's look at the derivative. So if I differentiate this once, right? So this will differentiate this, it will, a negative y will come down, right? So if I differentiate this again, this becomes negative ae minus y squared over 2, and then another negative y comes down again, minus y squared over 2, right? So this is going to be minus ae minus y squared over 2 plus y squared ae minus y squared over 2. Okay, so this y is large, so this is going to be negligible, and this part is approximately back to my original function psi, right? So that means yeah, so that means this is approximately equals to a y squared psi. So this, we have kind of verified this differential equation is satisfied like this when y is very far away. Okay, so this is what we mean by checking the asymptotic structure. We are just checking what happens if y is far away, so we are neglecting some terms, and this is the solution when y is far away, because yeah, it can satisfy this equation over here. So the math people looking at this will say that it is not very rigorous, is correct, right? But usually we do this kind of thing just to get an idea of what the solution is. We are not taking this as a solution yet, but we're taking this as a hint, as some information to help us guess a solution. Okay, so that is our first step. Okay, so we have some information of what happens when y is very far away. When y is very far away, the solution becomes like an exponential. Getting a feel for the solution first. Exactly, right? Yeah, we say it like a joke, but it's kind of true, you know? Like, when we want to solve an equation, we don't know what to do, so we do something, just get a rough idea or rough picture of what to do. That is pretty much, you know, what people do in research. So what is the feeling that we have? What we have here is we expect our solution to be something like, well, we don't know what is the solution yet, but what we do know is when y is large, it kind of behaves like an exponential y squared over 2. Okay, but what, yeah, of course, math people will say it's not rigorous. You cannot say this is the solution. It is not, but it is only kind of true when y is large. So what happens when y is not so large, when y is small? So then what you can try to guess is, well, we can say it's probably something times exponential. When y is getting very large, then maybe this will approach to a constant, then maybe this behaves like what we've seen earlier, and it will satisfy very far away. But when we decrease y, then this something might play a role. right? So now we kind of like narrow down, okay, what is this something now? So we don't know what it is unknown. So in general, let's call it some unknown function, some f. So this is what we call an ansatz, or a guess of how we can figure out the solution. Okay, so this is our initial guess, and sometimes when you read the literature, we call this ansatz, right? So ansatz is just a fancy word for guess, right? But we kind of guess based on some information that we did just now, right? We kind of like get this, okay, the solution kind of looks something like this, okay? But, well, if this is a solution, we must make sure it satisfies our ODE. What was our ODE? Our ODE is like this. So, well, to make sure this is satisfied, we need to plug this in, right? That means we need to calculate the derivative. So firstly, let us differentiate. So this is a function of y. So we don't know what this is. So let's just put it as df dy. And then y squared over 2. So by the product rule, I need to differentiate this thing as well. When I differentiate this thing as well, it just gives me a negative y e to the y squared over 2. Okay, so simplify this, because both terms have a factor of e, is just minus fy e to the power y squared over 2. Okay, so this is the first derivative. My ODE is a second derivative, so differentiate this one more time and see what happens. Do the product rule again. Okay, so differentiate whatever is inside, df dy square minus df dy times y, and then product rule, right? So minus dy df minus dy dy, so it just becomes 1, right? Y squared over 2. And then by the product rule, df dy minus fy, and then differentiating this gives me a negative y e to the power of y squared over 2. Am I right? Okay, so it's just 1 over here, right? So now let me simplify. The first term is second derivative of f. Okay, and then see, this is the same factor, so I'm going to put the exponential outside, but this is df dy y, then negative df dy y, so this is minus 2y df dy, and then I got f times 1, and then plus f times y squared. Okay, so I got this, and then simplify one more step. What I have here is df dy, and then is 2y df dy. This is positive y squared minus 1, factorize the f out, e to the y squared over 2. So this is my second derivative over here. So this is the second derivative, this is the function itself. Let us see what happens if we substitute into equation 1. Right? So we shall substitute into equation 1. What's equation 1 again? So equation 1 is the second derivative. So everyone's the second derivative here. df dy plus y squared minus 1f e to the y squared over 2. And then on the right hand side is y squared over lambda, then psi. So psi is e to the y squared over 2 again. Okay, so as you can see, right, we can also simplify this equation. Firstly, the exponential cancel on both sides, and then fy squared and fy squared, so this term also cancel on both sides. And then this is a negative lambda, I can just bring it to the other side. So I got second derivative df dy minus 2y df dy, and then plus the lambda. If I bring this over, it has a f, minus 1 has another f, so this becomes lambda minus 1 times f is equals to 0. Okay, so I now have another differential equation, this time for the unknown function f. Okay, so we kind of like guess this solution, we plug this in, and then we don't know what f is, we just know that it needs to satisfy this equation. So now our job now turns to solving this equation now. Okay, so now we need to solve this. To figure out what is f. Okay, so remember our mission, our quest. We want to find, well, if I can find f, that means I know what to put in here. Then I put in here, and this was the whole thing that we substituted. So if we can find f, we can solve the Schrodinger equation already. If we can find psi, it is a function of y, then all we need to do is to change everything back into x. Then that will be our solution. So everything boils down to finding f. Okay, so that is our like sub objective of our mission. Okay, any question? A to well, yes and no to normalize. In general, A can be any constant. Yeah, because when you have a differential equation, right, usually there's a constant in front. But just now we didn't even bother what was the A. Oh no. What's it? Yeah, unfortunately, most ODE is solved by like kind of like guessing. Because you know, most ODE are very messy and very difficult. And the ODE that you learn in your ODE class, right, usually they describe kind of like simple problems. So they have nice solution which you can derive from the beginning. But most of the time here we can't. So that's why we come up with all sorts of tricks to, so this is one of the tricks. And yeah, so like I said, right, all we need to do is just to find f. And let me remind you what was lambda. Lambda in terms of our original constants was this thing, right? And then our x was h bar m omega y, right? So if I can find this, then change everything back to our original variables, then we get our solution again. So if we can find f, we can ultimately solve the harmonic oscillator problem. Okay, so how do we solve this equation? I should probably keep the ODE here. This is one of a common method of solving. Okay, maybe you're learning this for the first time, but you will encounter this again in other places. What I'm trying to say is the power series method. In fact, we will use this method again in the future, later in this course, for the hydrogen atom. But we're doing it here first. Okay, power series method is just to let's say express f as a power series. Okay, so that is this method. That means f, right, we can imagine that this is a summation from 0 to infinity. Could be anything, could be any coefficient, and y to the power j, right? So what this means is this is the first term is to the power 0, the j equals to 1 is y to the power 1, 2 is y to the power square, c3 y3, and then y to the power 4, y to the power 5 forever. Okay, but cj may or may not be 0, so we need to figure out what is the cj. So we need to substitute this into the equation and make sure the right hand side is 0, right? So I got the f. I need to know what is the derivative as well. So df dy is basically just differentiating everybody here. So if I differentiate yj, the j come down, right? And then this becomes j minus 1, right? So if I write out every term, this is just going to be 0. This is going to be c1 plus 2c2y plus 3c3y squared plus dot dot dot, right? And then if I do the second derivative, all we need to do is just to differentiate this one more time. Well, the cj come down, differentiate another time, the j minus 1 also comes down, then upstairs becomes j minus 2. Okay, so this becomes 0, this becomes 0, this becomes 2c2 plus 6c3y, and then I don't know, whatever this is, right? keep on going. So now, if we try to say this is a series, well, does this satisfy the equation or not? All we want to do is just to make sure this whole bunch of stuff is equal to 0 on the right hand side. So we're going to substitute this into equation 2. Right, so the first one is the second derivative. So the first term is just the sum to infinity cj j minus 1 y to the power j minus 2, right? So that's the first term. And then the second term is minus 2y, and the first derivative, so the first derivative is 0 to infinity cj j y j minus 1, right? And then this term is the constant minus 1 is another constant, and then the f itself. So this f is just the sum from j0 to infinity cj yj. And I want to find the equations. The unknown variables are now the cj, right? So what are the values of c to make this right hand side equals to 0? So does everyone follow so far? Okay, so I better slow down before I jump into the next step. Let me see if there's any questions. Oh, a lot of interest. Oops, hang on. So ODE got taught the power series. Yeah, that is a linear differential equation. Yes, so it is kind of related to what we're doing here, kind of. Okay, in a sense that all these are going to be the eigenstates of the Hamiltonian, right? So ultimately they can be related in this way, and then we got superpositions. In the same way we can superpose those kind of things. But okay, so if everyone follow the story until now, let's continue the next part of the story. So I'm going to manipulate this equation a little bit just to, again, to simplify this as much as I can. Notice, look at this thing, right? So this thing, right, this is the second derivative. The first two terms is 0. So when j equals to 0, when you plug this in, you get 0. When j is equals to 1, you plug this in, you get also 0. So the first non-zero term starts from j equals to 2. Okay, so let me write this out. Okay, so we make the observation that the j0 and j1 terms are 0. So the first non-zero term starts at j equals to 2. So what I'm going to do is I will, so actually the first term starts j equal to 2. So I'm going to just change variables a little bit. I'm going to call k equals to j minus 2, so that j is equals to k plus 2, and then my sum starts from k equals to 0. Do you agree? Right, I'm just, instead of calling this j, I substitute k as k plus 2. So what this happens is, my summation is k from 0 to infinity. This is ck plus 2. This is k plus 2 and k minus 1. Right, so I'm not doing anything special. I'm just calling this j minus 2 as k only. So nothing special here. Okay, so nothing special here. And then now I want to manipulate this term now. Okay, so let me make some space to avoid confusing each other. So for this term, right, there is a y and there's a sum over j minus 1. So I'm going to multiply all the y inside and just multiply the 2 as well. So I'm going to multiply the negative 2y inside. So if I multiply the two things inside, so the term becomes the sum from j0 to infinity and then I got Cj. The negative 2 goes inside, and then the y times this y is going to be y to the power j. Okay, so this one, everything is correct. The sum starts from j, okay, where sum starts from j0, but this is a y to the power j, right? And then what I'm going to do next is, well, I want to compare with this later, so I'm going to just rename this as k. J, I'll just call this k, so that this summation is now k from 0 to infinity, ck minus 2 ky to the power k. Okay, now since I'm changing everybody to k, might as well change this to k as well. So I shall also rename this to k. Firstly, of course, I will multiply the constant inside, and then rename the variable, rename the index, right? Instead of j, I'll just call everything k, so that this thing is just the sum from k0 to infinity, ck lambda minus 1 y to the power k, right? So this is my first term. I manipulate to look like this. The second term, I make it into this, and this is my third term. This plus this plus this, and the whole thing should be equals to 0. Okay. Oh, plus 1, sorry, you're right, plus 1. Okay, so yeah, so since you asked this, it kind of gives a hope that, yeah, everyone's following the story, which is good news. Now we shall continue. Okay, so since we change it into this form already, the whole equation becomes this now. So I got k 0 to infinity, ck plus 2, k plus 2, k plus 1, you are right, y to the power k. And then this is a summation from k 0 to infinity, negative 2, and then there's a k ck y to the power k. This is a summation. So I make everything the same, so it's easy to look at later, right? Is lambda minus 1 ck y to the power k equals to 0. Okay, so notice that now every term has a summation with the factor of k, so I will factorize the y outside. Okay, so this whole thing, and everyone sum from k equals to 0, so that means I can just do this whole thing over here. Okay, and then I got k plus 2, k plus 1 ck, and then this is minus 2k ck, and then this is plus lambda minus 1 ck. The k is here, here, and then the y is factorized outside, y to the power k. Okay, and then again, these two terms are the same, so this one also can be factorized. So this becomes the summation from 0 to infinity, k plus 2, k plus 1, minus 2k plus 1 minus lambda. Right, I take out the minus, I take out negative ck. So the ck goes out, and then everybody times y to the power k. This whole thing is equals to 0. Okay, so now my equation has now been I forgot, this is ck plus 2, ck plus 2, I forgot to write this. Okay, yeah, so now this is page 3. Oh yeah, you told me, yeah, this one, right? Okay, good. So seems like most people are following, at least following this better compared to the algebraic method, right? And yeah, like as we have seen just now, this is a more traditional way to solve this. So it's consistent with our expectations. So how do we make sure this equation is satisfied? How do I make sure that this whole thing is equal to 0? Well, this will definitely be equal to 0 if every term in the square bracket will be equal to 0, right? So that is our way to solve it. So this equation is, the equation will be satisfied if every term in a square bracket are actually what we call the coefficients of the y to the power k. So if each coefficient of yk is 0, right? In other words, everybody here is 0, then the whole summation is 0, then the equation will be solved. That is what we want, right? So can we make this 0? So we got this now, plus 2 minus 2k plus 1 minus lambda ck equals to 0. So we got this equation with k. Remember, k is the index which goes from 0, 1, 2, 3, 4, 5. But in any case, we got some relation between ck minus 2 and the previous 2ck, which is 2k plus 1 minus lambda divided by k plus 2, k plus 1, ck. Okay, so this is not an equation to determine the c, but this is what we call a recursion relation. Given the k, I can determine the next, the 2 steps later of the c. Given 1 c, I can determine the c at 2 steps later. Okay, but this is in terms of k, right? Our original expression was using j, so let's just change it back. Rename w index back. Okay, so this one is not important, it's just to like your personal taste. Some people prefer to use j because it looks nicer on paper or whatever reason, but I'll just change it back to j. Okay, and of course the j depends on cj. So the j is 0, 1, 2, ... Okay, so we got this now. Remember what was the cj are about? The cj are the coefficients in my power series, right? So this is summing from 0 to infinity cj yj. So we have found a relation for the cj. Well, it's not a, we don't know how to determine the individual c. We just know how this c relates to another c. This is what we call a recursion relation. Okay. Okay, so the question Wei Zheng is asking why the equation is satisfied if all the coefficient is 0, because we have manipulated we have reduced our equation into this, right? So remember how did we do this? This was our differential equation was this, but if I write f as a power series, then this one is a summation with cj, this is another summation, this is another summation. So we substitute everyone inside, right? We substitute and then we simplify until we got this. So we got the square bracket times yk equals to 0. And what we just want to do is to make sure this equation really is equal to 0. And one way to make this equal to 0 is the term inside the square bracket is equal to 0. Why cannot be 0? I think that was Chiri's comment, right? If y is 0, yeah, correct. Is linearly in, y cannot be 0 is because y is our variable of our harmonic oscillator, right? Our harmonic oscillator is about half kx squared, and we want to know what is the force experienced by the particle at this x, at this other x. If we just say y is equals to 0, that means x equals to 0. That means we just got information at one point of the system only, right? If y is equals to 0, that means if I plug in, it just means that we don't we cannot get the wave function as y. right? We want to have a solution that is a function of y, not just y equals to 0. Make sense, right? Because y is my variable. Okay. So yeah, so that's why we avoid saying y is 0, because it doesn't tell us anything. We want a wave function that is a function of y. So we don't want to just force the whole y to be 0. Okay. Good. Follow so far? Yeah, so this was what we were discussing. Yeah, correct. The 0 comes from the ODE, because it's an ODE, but we push everything to the left hand side, and then what is left on the other side is 0. Yeah, so let me a quick recap, right? This was our original ODE, right? We changed into this form, and then we say this. So we plug this into the ODE, we plug this into this, so that we got this now, and push everything to the left hand side, so the right hand side becomes 0. And this is manipulated into this. And how do we want to make this true to be 0? We say the y bracket 0, so we arrive at this recursion relation. So that is our story so far. But let's kind of like take a look at a few of the terms over here. Okay, so let us plug in a few j. If I put in j equals to 0, right, what do I get? So if I put in j 0, this will give me j2, c2, right? And then if I put in j0, it's just 1 minus lambda, and then I got 2 times 1, so it's 2, and then c0, right? So we do not have a formula for c2 alone, but it's expressed in terms of c0. Let's see what happens if I put in j1. If I put in j1, I got c3. Then if I put in j1, so it's 2 plus 1, so it's 3 minus lambda, 3 times 2, so you got a 6. And then j1, right, so it's c1. See, this one depends on c1 itself. Okay, so let's look at j2. So if I put in j2, then this will give me c4. j2, it will give me 4 plus 1, so 5 minus lambda. 4 times 3, 12. j2, right, so c2. So c4 depends on c2, but c2 itself, I can put it in here, right? So we notice this. That means c4 ultimately depends on c2, and everybody ultimately depends on c0. So this is 5 minus lambda, 1 this, and then this is 24, c0. So c4 depends on c0. Okay, so you kind of, hopefully you can notice the pattern over here. If I put in j3, then this will give me c5, and then I'm lazy to work it out. Let me look at my notes. C5, 7 minus lambda, and then this is 20, c3. See, there's a c3 coming up here. So the c3 depends on c1. So I can put this into here, and then I will simplify. I will just skip the steps. These are boring stuff. You're gonna get 7 minus lambda, 3 minus lambda, and then this is 120, c1. So let me write one more. This is c6, right? So c6 is going to be 9 minus lambda over 30 times c4, but c4 depends on this. So after some simplification, you got 9 minus lambda, 5 minus lambda, 1 minus lambda. This is 720, c0. So you notice the pattern so far, right? Everybody depends on either c0 or c1. So even though there's many c in our recursion relation, we can trace all the even number c to c0, all the odd number c back to c1. So our final solution just depends on these two numbers only, which we still haven't fixed yet. We still don't know yet, but at least we kind of narrow down. Instead of infinitely many constants we need to solve, actually we just need to figure out what are the two. So C0, C1 always 0. If I put both 0, then everybody 0, then that means f is equal to 0, then the wave function is equal to 0. So you just get nothing. It just gives me 0 equals to 0. Okay, so we want to find a solution that is non-zero. Yeah. So let me just list this down. So for j even, just to emphasize this, we got a C0 and C1 was 1 minus lambda over 2 C0, hang on, C2. C4 is equals to 5 minus lambda 1 minus lambda over 24 C0. C6 was 9 minus lambda 5 minus lambda 1 minus lambda 720 C0, and you can keep on going. So you notice that we realize that the C of even number, right, depends on C0. Okay, so all the even number here, it depends on C0, and the odd number will depend on C1. So if j odd, right, the first odd number is C1, and then the next odd is C3. So C3 was 3 minus lambda excuse me, and then C5 was excuse me, 7 minus lambda 3 minus lambda over 120 C1, and then when you go to C7 is 11 minus lambda 7 minus lambda 3 minus lambda over 5040 C1. So all the C of odd number depends on C1, right? So C0 here, C1 all here. So C0 controls all the even number coefficients, C1 controls all the odd number coefficients. Okay? Oh, thanks. Correct, yes. Yes. So ultimately C0 and C1 are the integration constant, because remember, right, in ODE you learned that second order differential equations will give you two constants. These are my two constants. Okay, and then once you got the solution for each individual one, then you can use superposition to create new solutions. Because in ODE you have also learned about the superposition, right? Superposition in ODE is the same reason why we have superposition in quantum mechanics, because quantum mechanics came from Schrödinger, which is also a ODE. Okay, but now, well, here's the problem. Again, let us check the asymptotic structure. We don't know what is C1, C2 yet, but we seem to have an infinite series of C, right? Odd number C, even number C. We seem to have an infinite series. And I want to show you that if it's an infinite series, the solution is not normalizable. Why? Let us check. So now check what happens. Again, we look at the asymptotic structure. What if J is large, right? So let's say C very high, C to 1,000,000, right? C 1,000,000 and 1, C 1,000,000 and 2. What's going to happen? So if you look at our formula for C, if J is large, then this term is big. This term is going to be negligible. J can be as large as you want. These are fixed numbers. So if J continues to be large, these two terms are negligible. So this becomes 2J over J squared, right? So Cj plus 2 is approximately equal to 2J over J squared Cj. So this is approximately equal to 2 over J Cj, right? So we're just checking what happens when the J is large. Okay, for reasons that will be clear later, but let me just show you what happens if J is large. So if j is large, Cj is approximately this, right? Plus some small numbers which just changed by a little bit, but never mind. But this Cj itself, I can use the formula again, less by 2. So 2 over j, Cj is itself 2 over j minus 2, Cj minus 2, am I right? And then Cj itself, I can apply the formula again. This is 2j minus 4, Cj minus 4. So you can keep on applying the formula, which I will do until because j is very large, so you can keep on going down, going down, going down. But let me put the 2 downstairs here. So if I put the 2 downstairs here, this becomes j over 2 minus 1. If I put the 2 downstairs here, this becomes j over 2 minus 2. And then I keep on applying the formula, and then I keep on bringing the 2 downstairs. So it will be keep on going. So what does this formula looks like? This is j minus 2, j minus 1, less. This is the original number, less by 1, less by 2, and then I multiply everything together. So this is actually something like j over 2 factorial. Okay. And then this whole thing was supposed to be Cj minus 2, right? So Cj minus 2, I would further argue that since j is large, j plus 2 is still close to the j, so this is like Cj, right? So this is my asymptotic structure for the Cj for large j. Why do I say asymptotic structure? Asymptotic structure is for large y. This is j, but they are the same because for large y, the higher powers of y are important. So they dominate. So that means when y is large, the important terms are coming from the large j numbers, right? So let's look at what happens to my series of f. So my series of f originally is just the sum of Cj, Yj, right? But when I look at large y, the large j points are important. So the Cj becomes this. So it is approximately the sum over j over 2 factorial Yj, right? And then let me do one more step. I'm going to change the index again. I'm going to let k is equals to j over 2, so that j is equals to 2k. So this becomes a sum over k, 1 over k factorial, and then this is y to the 2k, right? And what is this? So y over 2k is just 1 over k factorial, y square to the power k. Now, what does anyone recognize this sum? This is actually the sum of an exponential series, right? So this is the formula for the exponential of y squared. Okay. Any questions so far? Yeah, it doesn't matter. When j is large, yeah, because when j is large, right? So the last digit of j is not important. Yeah. Kind of, yeah. The asymptotic analysis is kind of this kind of thing, right? We don't really, yeah. Whether j is even or odd, it's a large number, right? So if I have $1 million, do you care whether this $1 million is it an even or odd number, right? If you're talking about $1 million, you lose $1 become odd number, it's fine, right? You just lost $1. It's still like almost 1 million. So it's not important whether even or odd. So that's not the main point. The main point is, it is kind of like an exponential solution. But then, hang on a minute. If y is large, this becomes the exponential solution again, which was, we already had an exponential solution. We already had the exponential solution. Now you're saying this is also another exponential. So if by this logic, right, we continue on, this gives for large y, right, we're talking about large y, right, so e to the y square. So my wave function itself is supposed to be fy e to the y square over 2. So if you're talking about large y, okay, asymptotic analysis, then this becomes, it's going to be some constant, but it's just e y square e to the negative y square over 2. But this term is equals to positive y square over 2. So this is going to be infinity if y goes to infinity. If this is true, then this is not normalizable, right? So if this is true, then we encounter a problem. It is not normalizable. Because if we try to integrate from let's say x, because x you can change it to y, right? It doesn't matter. Well, we are still integrating from infinity to infinity, then it's gonna be infinity. So there's gonna be a problem. Okay, so we encounter a problem now in trying to solve our Schrodinger equation using the power series method. And we already, so this is why we did asymptotic analysis. We already identified this problem just by looking at large j. We didn't need to calculate all the individuals j. We just say that if j is large, this is going to happen. This is going to happen. And we identified the problem right then. Okay, so yeah, so now I guess now it's a good cliffhanger. So we can take a 10 minutes break and we can continue to see how we overcome this problem after this. Yeah, so to answer your question, Rachel, it doesn't matter. J is just some large j, basically some large j. Right, and we are not again, right, let me emphasize, what is the from j what to what, we don't really care, right? It just means that if j is large, it's gonna be whatever this limit is, it's gonna be close to the exponential, and that we already identified the problem. So we kind of like extract information without getting exact values for the j. All we need is j large. So that is the problem here. So yeah, let's take a 10 minutes break. And yeah, this one is kind of like a episode, right? So we take a 10 minutes break, commercial break, at the plot twist, and then we come back after the commercial break. What's it called? Schrodinger's cat and the Raiders of the Lost Quark. And it seems like everything is about the physics. You play as the Schrodinger's cat itself. And then your quarks are your power-ups or something. I have no idea. Okay, so there's not outside is very noisy right now, but I hope everyone can still hear me. Is it running? Okay, recording. Okay, yeah, full screen. So our problem is well, we encountered a problem. Even though we tried to do a power series, it seems like we're kind of like wasted our time, right? At the beginning, we did the asymptotic structure. We know that when y is large, is exponential y square. Okay, then we keep that part. And then we focus on this something part, which is f of y. And then we try to figure out what is f of y. And then we went through all the calculation. F of y is another exponential, which makes the whole thing not normalizable. Exponential with a positive power. Exponential of positive y squared. So when y goes to infinity, the exponential goes to infinity. Another exponential. So how do we handle this problem? So this is the thing that we want to address now. How to solve this issue. Okay. So one thing to take note there is that let me double check the recording again. Yes. So one thing to take note is that we have identified this issue that happened because, where was it? Because y is large. Mixing up the pages. Yeah, so yeah, we didn't even care what is the limit of the summation from what to what, don't know, as long as it's large, right? So the problem happened when y is large. So we have this problem when j is large, right? So when j is large, Cj, we say that it's approximately j half factorial, right? And so yeah, that means when j is large, we sum to infinity. Another way to rephrase what we just got was that the infinite series, okay, so this infinite series is approximately an exponential. Right, so f of y, when y or k is large, we change this to k, 1 over k factorial e to the y to the 2k, right? So this becomes e approximately e to the y squared, which is not normalizable. Okay, so the argument goes that I say that this is like an exponential is because when we had an infinite series we learned in calculus, if you sum to infinity, it converges to an exponential function, right? Only if you sum to infinity. And this is where we had the problem. So how to avoid the problem is, let's not sum to infinity. So we avoid this problem. If my function is not an infinite series. Right? So yeah, if it's an infinite series, we got this, then we got this. So now that means we know what to avoid. So maybe we'll try to avoid this by not having it an infinite series. Okay? Which is to say that if we do not sum to infinity, it is a finite number of terms. So f of y, right, usually, yeah, you start with c0 and then c1y1 plus c2y squared plus c3y3, okay? Do not sum to infinity, you stop somewhere. We stop at the nth power. Okay, so we stop here. So anything higher is going to be 0, 0, 0. Okay, so this is one way to avoid it from summing to infinity. Okay, so we stop here. Therefore, this is going to be my last non-zero term, which is to say that Cn is my last one. Okay, so everybody here, some of them may not be 0, some are 0, fine, whatever, but the last one is here. Definitely everyone here, I must be 0. So the next number, Cn plus 1, I want this to be 0. Cn plus 2, 0. Cn plus 3, 0. Everyone 0. Okay, all 0. So can we make this possible or not? Right? Can we achieve this? Because notice that C, all this C, right? Our C at the end of the day is still depends on this recursion relation, which I shall call this equation 3. Right? Just now 1, 2, now 3, right? And let me just copy this down again. Cj plus 2 is equals to 2j plus 1 minus lambda j plus 2, j plus 1. And Cj. Okay, so we got this now. Can I make, so this is a possible way to fix our issue, but can we do this or not? We still foresee a problem, right? The j minus 2, j plus 2 depends on the previous j, and this will depend on the previous j, So how can I make this 0 but I keep all this stuff here? Is it possible or not? It turns out that yes, we can. Okay, notice that, okay, so Cj, right, and then Cj plus 2. This is my last term. So if this is my Cn, which is not 0, can I make, using this formula, can I make this 0? So let's start by, at the first step, let's try to make Cn plus 2 0. Okay. So using the formula, using equation 3, by plugging in j equals to n, right? N is some fixed number. So Cn plus 2 is 2n plus 1 minus lambda, n plus 2, n plus 1, and then Cn. So as like I said, okay, so you're talking about Valorant guns, right? So as I mentioned just now, this one definitely not 0 because it's the last one, the last non-zero term. So this term is not 0. I want this to be 0. So can I make this 0? Well, maybe this thing is 0. Right? So yeah, it is possible because lambda is a constant. And we haven't decided what is the value of this constant yet. So maybe I can make this term 0. So if lambda is equals to 2n plus 1, right? If lambda is equals to 2n plus 1, then I sum until here, I hit lambda equals to 2n plus 1. J increases from 0, 1, 2, 3, right? Until I reach j equals to n, lambda equals to this, n, and this becomes 0. So I will make this term 0. So if I can make this term 0, then the Cn plus 4 is going to be 0 as well. And then Cn plus 6 is going to be 0. And all the even number, Cn plus even number, all the alternating terms are going to be 0. So that part settled, at least half of it. Right? So this part settled. Right? So this part settled. Now let's look back. Okay? We have if this is satisfied, then half of these terms are 0. Fine. Then let's look at the previous terms. So Cn is not 0. So what is Cn minus 2? So because Cn is not 0 and we have also decided that lambda must be this number to make sure all these guys are 0. Then using equation 3, it says if I plug in j equals to n minus 2, then my formula becomes Cn is equals to 2n minus 2 plus 1 minus lambda, n minus 2, so it's just n minus 1. Then this is Cn minus 2. Okay, so let me simplify this. This is 2n, 2n, actually it doesn't matter. 2n minus 4 plus 1, so it's minus 3 minus lambda, n minus 1, Cn minus 2. Right, so lambda was 2n plus 1. So it cannot cancel this. Right, so this part is, this stuff here is not 0. Okay, and this part here is the last non-zero term. So this part is also not 0. What does this tell me? This tells me that if Cn is not 0, then Cn minus 2 is also non-zero. Right? This equation must be equal to this. Nobody here is 0. Okay? So that means Cn minus 2 is not 0. And then you can apply the same equation again with Jn minus 4. Then Cn minus 4 is not 0. Cn minus 6 is not 0. Everybody is non-zero until the smallest term. Right? But the smallest term is which one? C0 or C1? It depends. Okay? So this is page 6, right? This is page 7. So our conclusion is that because it depends on Cn. Now, if Cn is an even number, if n is an even number, we have concluded that Cn is the last non-zero term, so it's not 0. Cn minus 2 also non-zero. Cn minus 4, right? If n is an even number, where will it stop? right? It will come down to, if it's an even number, right, everyone here are even, so C4, C2, and then C0. So all these are non-zero. Okay, so in other words, if n is an even number, if the last term is an even power, then all even coefficients non-zero. Agree? Totally makes sense, right? That is really, E is an even number, right? Let's say n is 16, right? So 16, 14, 12, 10, 8, all the way until 0. Now, if n is an odd number, then of course, yeah, this is the last non-zero term, so Cn non-zero. The next odd number also not zero. The next one non-zero. But if this is odd number, this is also odd. That means I come to C5, C3, C1. The final one is C1. So all these are non-zero. So if n is even, all even coefficients non-zero. If n is odd, all odd Cj are non-zero. Okay? So we have kind of figured this out already. We have extracted at least this much information just by making Cn plus 2 all 0. So if Cn plus 2 is 0, 0, 0, 0, but if you go backwards, the even ones are non-zero or odd ones are non-zero, depends on the n. Okay, but we haven't done this yet, right? How about the n plus 1? If I can make n plus 1 0, then this is going to be 0. Then the n plus odd number, so n plus 5 also is, I can also make it 0. And so on and so forth. So can we make this 0 as well? Let's try. Okay, so if we do this, so this is the next part. We are making Cn plus 1 equals to 0. Oh, how did I write this? Yeah, so this. Okay, so this is the next point. So if I want to make this 0, then I use equation 3 with j equals to n minus 1. So if I plug this in, right, what was my equation 3? J equals to n minus 1, so this will become Cn plus 1. Right, we want this to become 0, but this 2n minus 1 plus 1 minus lambda, and then this becomes n plus 1, and then n, and then this is Cn minus 1. Okay, so so notice that if I simplify this, right, this becomes what? This is 2n minus 2 plus 1 minus lambda, n plus 1, Cn minus 1. So minus 2 and 1, it becomes 2n minus 1 minus lambda, n plus 1. Okay, so the formula of Cn plus 1 depends on Cn plus 1 depends on Cn minus 1. And I want to make sure this is 0. Right, so can I make this 0 or not? Let's look at this. This one cannot be 0 because we already say lambda is 2n plus 1. Right? So we already say this to make n plus 2 0. If I fix this already, then this one cannot be 0 anymore. Okay? So how can I make this 0? So the only way is to have Cn minus 1 0. So make this 0. So this will be 0. Right? So if this term is 0, then Cn minus 1 is 0. Right? So Cn plus 1 is 0 if Cn minus 1 is also 0. Okay? Then this one we can apply equation 3 again. So how do we make sure Cn minus 1 0? So this one is 0 if Cn minus 3 also 0. Right? But how do we make this 0? So yeah, we can go on forever. This is 0 if Cn minus 5 is 0, and so on and so forth. So we come to the same reasoning now. Just now we argued that all these are non-zero, but because of this, all this must be 0. So if n is even, right? So if n is even, we know these are non-zero, but how about Cn minus 1? So Cn minus 1, Cn minus 3, Cn minus 5, all the way even, right? Where does it stop? If n is even, that means I got the odd number. So all this, everyone here are odd numbers. C3, C1, all must be 0. Okay, so all odd Cj are 0. Then the same situation for the odd case. Right? So if this is an odd number, that means Cn minus 1 is an even. Then n minus 3 is even. So everyone here are even. So I got C4, C2, C0, all 0. So it depends on the value of the n. So all even Cj are 0. Do you follow so far? Okay. So we are trying to solve our problem, right? We are trying to solve the differential equation. The differential equation is satisfied if this. But we notice that, you know, it cannot be any coefficient. For large j, it becomes an exponential. So to avoid this, we make the summation stop somewhere. To make this stop somewhere, I want to make everyone after this 0. And how did I make everyone after this 0? Well, the first choice is to choose lambda equals to 2n plus 1. Okay, so if lambda is 2n plus 1, then n plus 2 0, n plus 4 0, n plus 5 0. And then the other ones have to be automatically 0. Okay, so let me write everything what I just said out. So in summary, in conclusion, or in summary, yeah, so in conclusion, right, so we have chose lambda to be 2n plus 1. N is a fixed integer, right? So n is some fixed integer. Okay, it's not a variable, it doesn't depend on y. But if n is even, then what did we say just now? That the even Cj are non-zero, the odd Cj's are going to be 0. So that means my series is just consists of even terms only. So C0, C1 no, C2 y2, C3 no, 0. So C4 y4 plus this until the Cn yn, where this is the even number. So everyone here have even powers. Okay. Then if n is odd, then fy C0, well, is 0. So the first odd power is y to the power 1. C2, no. C3, y3, C5, y5, until the last one, which is odd. So over here we got odd powers only. Okay. Oh, you're talking about brain explode. But I hope everyone is following so far, right? So at least now we don't, this one definitely we do not have the problem of the exponential, right? Because we do not sum to infinity. There's no such thing as large y or large j. Well, y can be large, but there's no Cj large. When there's no Cj large, this summation cannot turn into an exponential. So maybe this one can work. So we can have this, right? And it will be normalizable because it's a finite series. So it's a polynomial. So we can, if it's a polynomial, we can plug it into our wave function psi. We can integrate this, you get some number, and whatever the number is, we can choose a constant to make the integral 1. But let me show you this part. Let's come back to the lambda, right? So we chose lambda to be 2n plus 1. Recall what was lambda. Lambda is just a constant which we call to simplify our constants, right? Where was it? Lambda is 2e over h bar omega. Right? So we are saying that 2e over h bar omega is 2n plus 1, and the n are integers, right? Some fixed integer, whatever fixed integer. Because it's just the power of this. And then, yeah, if we rearrange this, we got h bar over 2, 2n plus 1, then we get something familiar. If we multiply the 2 inside, we got n plus half, and then we got h bar omega. So we kind of accidentally recovered the energy levels of the harmonic oscillator, just because we wanted to make the series finite. So yeah, suddenly we got this, which is a pleasant surprise, am I right? So we recovered the energy levels. Yeah, me, I have no idea what you guys are talking about. So now we kind of like almost got the solution. Actually, we have solved the solution already. We C0, C2, C3. Remember that we have a formula to determine, right? So C2 depends on C0, C4 everyone depends on C0. These are the constants which we have the formula already. So we have kind of solved the problem already. So this is our solution. Right? Our solution to the original problem that we started with, our harmonic oscillator problem, which we say this, and our solution was, well, our wave function psi, we have expressed this as depending on y, right? And then this was the asymptotic behavior, y squared over 2, right? And now we know that well, this f is a polynomial in n, and to change back to our original variables, we just change everything back to x, and the lambda was 2e over h bar omega, which gives e is equals to n plus half h bar omega, and n is equals to 0, 1, 2, 3, dot dot dot, right? And this f could either be an even or odd number. So it depends on the n, right? So this depends on n. Physically, it depends on the energy level. So for the nth energy level, whatever this n is, start from 0, next is 1, next is 2. This n depends whether it's an even or an odd number. So if it's an even number, then the series looks like this. If n is even, if n is an odd number, the series starts from C1, C3, Y3, until some odd number Cn, Yn. And how do I determine the C, right? So C0, 2, 4, dot, 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 it depends on our recursion relation. So Cj plus 2 is equals to 2j plus 1 minus lambda, j plus 2, j plus 1 depends on Cj. So the first one is C0. If it's even, then let's say n equals to 4. Let's say I want to find the solution for the fourth energy level. Then I got C0, C2, and then C4. So I use this to determine C0, C2, C4, right? And then once I got this polynomial, I got the full solution, right? And then as a final step, just change everything back to the function of your original variables, and that is our solution to our harmonic oscillator. right? So the remaining free parameters are the C1 and C2. So I'm gonna write it here. Well, it's either C0 or C1, right? Seldom both together at the same time. So this can be determined by normalization. Okay, but in any case, yeah, we have everything we need to solve the harmonic oscillator already. So this whole thing was our solution. Okay, follow so far? What, you guys okay? Correct. So are you talking about we spent 2 hours doing the power series method, even though the previous class we spent the algebraic method, right? Yeah, because we had to, right? Especially since a lot of you were lost using the algebraic method. Okay, but the power series method, even if you already know is a good application. We will be using this method again later, and still the power series method. So it's a good, at least a good practice. So now let us construct some explicit solution. Some explicit solution. I do also think in the mind-blowing sense is that we use 2 totally different methods from 2 different branches of math to solve the same problem, and we got the same solution, right? So things that look totally different. Remember last week we are doing like creation operators, annihilation operators, and all those stuff. And we got the wave function. We got the wave function there, right? So now let us see if we can recover the same wave function. They should be the same, right? We are solving the same problem, just that the methods are different. So let's try to solve this, the ground state of the harmonic oscillator. What was the ground state wave function? Last time we did this before last time, we got the Gaussian, right? The bell curve. So for the ground state, the energy level, if you use the formula that we got the same formula here. The ground state is just half h bar omega, right? And then this is n equals to 0. So n is equals to 0. What's my Fy? So Fy is just C0 alone, right? Nothing else. This is already the last non-zero term. Okay, so that means, so that's it. That means my wave function is supposed to be e minus Fy squared over 2. Let us put everything back. So my F was C0 and y square. Y square means the square of this. So this is actually m omega x square over h bar. Y square over 2, so there's a 2 h bar, right? So yeah, then this is the same solution that we got last time, right? Just that last time we call this A, right? And we determine the constant by normalizing. So we get C0. We did this last week already, so I don't want to do it again. M omega over pi h bar to the power of 1/4, right? So this express everything in terms of x. We got the ground state wave function for the harmonic oscillator, which is m omega over pi h bar 1/4, and then the Gaussian m omega x square over 2h bar, right? So this was what we did last week using the operator method, right? So pretty cool, right? We got the same thing again, but in a totally different method. This one is using the power series solution. Yeah, right? So it's kind of like interesting way. We had a problem. It's almost like a 3-act structure. We had a problem, and then in the middle during the break, we face a challenge that's usually in the middle of the movie. We encounter a problem, right? When the hero like nearly die or something, and then finally we need to overcome the final challenges to get this. But yes, it tends to happen that you forget what we were doing. Once we spend so much time doing the math, we forgot our original problem, right? So it's good to remind ourselves every once in a while. Okay, so yeah, so now the next thing that we want to do is, okay, we got the ground state. Can we get the n equals to 1 state? Right? So this is the first excited state. So when n is equals to 1, what was my energy? So if I put in n equals to 1, you got 3/2 h bar omega. N is an odd number, so f of y, well, all this is just c1 also, right? But c1 is c1 times y to the power 1. So only one term, but the power of y is 1, right? This one, the power of y is 0, so it got a constant. The power of y is 1. This is a linear term. So what happened to my wave function? So my wave function is supposed to be this, right? So this was what we did whereby our asymptotic analysis. Then our f now we know our f is just c times y, e to the y squared over 2. Okay, so let's try to put this back in terms of x. Remember what was y? Y was the square root of m omega over h bar times x, and then this whole thing was m omega x squared over 2h bar. Okay, so now we determine c by normalization. So now let's try to normalize this. Okay, so normalize. What time is it now? Okay, plenty of time, so I can do it slowly, because this part is going to be tricky. More math, but we kind of got the physical solution already. In any case, the integral of this function with respect to dx must be equals to 1. Right, and I did have a few questions already, so I tend to forget to say that sometimes I'm lazy to write the limits, but in quantum mechanics, the integral must be from minus infinity to infinity, right? So yeah, let's try to work this out. So this is the absolute square. So how do we get the absolute square? Well, absolute c1 square, the first thing here, squaring this is m omega over h bar, squaring x square. If I square this, it will become m omega over h bar x square. Am I right? Okay. The 2 will disappear after you square it. So let me move the constants away. So got m omega over h bar, absolute value c1 square, and all I'm integrate with respect to dx. So what I want to do is I want to integrate x square e to the power of m omega over h bar x square with respect to dx, and this whole thing must be equals to 1. Okay, so how do you work out this integration? So don't worry, this is not a calculus class anymore, so you will not be tested on integration by parts or thing. In fact, this one does not have an antiderivative. What we do have is our integration formula list in the lecture notes. So we go to this page here, right? So let's just make use of this Gaussian integral. Okay, so in the lecture notes, we have the convenient handy formula for anything with the exponential. So in our case, n is equals to 1, so this is x squared, and then there's a a squared. So this a squared will come out in the solution over here. So to compare accurately, this is where you have to be careful. Even though we got a formula, we must be careful, right? So according to this part is 1 over a square is equal to m omega over h bar. In other words, your a itself must be h bar over m omega. Okay, so what is this integration now? So this integration, according to the integration formula, right, this is my a, it is 2 root pi 2n over n factorial, but n is 1. So it is 2 root pi, n is 1, so 2n over n factorial is just 2, right? And then is a half to the power of 2n plus 1. So n is 1, so this is to the power 3. There's a half, right? So a is this thing, so it's h bar over m omega this thing. Okay, so it's not difficult, just that there's a lot of constant you need to be careful. Okay, so yeah, so let's try to work this out. Okay, so this equation tells me that 1 is equals to, I also must be careful. I'm also not good at doing this calculation. I need to check many times before finding mistakes. But at least this part is here. Then 1 over 2 to the power 3, so it's just 2 times 2 times 2. And then h bar over m omega. So h bar over m omega square root and then to the power 3, so it's to the power of 3 over 2. Right? So we can cancel 2 of these. And then there's a root pi, there's a 2, nothing I can do here, so let's keep it here. There's a c1 absolute square. And then I got m omega over, so notice that this is the upside down of this. So actually what we're having is h m omega, this is the upside down, so this is 3 over 2 minus 1. So that means this is just pi over 2 c1 square h bar over m omega half, right? Okay, everyone follow so far? One dimension. Okay, we'll come to that later. Yes, you're right. Chapter 4 is nearly the end. Chapter 4 is just solving harmonic oscillator using these two methods. Chapter 4 is a short chapter for harmonic oscillator. But chapter 5 is the 3D. We'll come to that after we finish this, right? So it's still halfway. But our equation now, let me write this one more line. Pi over 2 h bar over m omega half. So I want to solve for C1, right? So if I bring everyone over, I got 2 over root pi. 2 over root pi. And then I got m omega over h bar. So this is the power half. This is another root. So this is actually 2 m omega over pi h bar, the square root. Okay, so I hope I didn't make any mistakes. But let me choose the C1 to satisfy this condition. So if C1 is a real number, then we just need to be the square root of this side. So this is just m omega over pi h bar to the power of 1 over 4. So we have found C1 like this. So we put this back to the solution. But what was it? My wave function was what? We found the C1, right? And then we got the m omega. So what we have here is root 2 m omega over pi h bar to the power 1/4, and this another m omega over h bar root x e to the power m omega x squared over 2h bar. So the square root, let me put everything inside. We have found 2 m omega over h bar square root and then m omega over pi h bar 1/4 x e to the power of m omega x squared over 2h bar. So yeah, we did it. If you recall, this was exactly the first excited wave function that we did using the operator method. Using operator method, we operate the creation operator to the ground state we created into this, and then we manipulated until we got this solution, right? But we recover the same solution again using the power series method. Okay, so yeah, that's pretty cool, right? Okay, so it's n is the nth energy level, right? So n is the nth energy level, right? Because we got En is n plus half h bar omega, right? So n is 1, 2, 3, 4. N is the integer. Now, so we have gone through so much trouble, but we just found psi 1, right? And generally, n could be any number, like we are saying just now. N is any integer, okay? So psi, this is n equals to 1, just now n equals to 0. But for any n, we notice that it's going to be, well, if you notice the pattern, right, it's going to be some constant, and then it's going to be some polynomial of degree n, and then times e to the y squared over 2, right? So this constant will be like c1 or c0, and then we fix it by normalization, which is what we did in the previous two examples, right? And if you look up the solutions, there is a general expression for it, 2nn factorial square root, right? And then this is inside here is a polynomial of degree n, right? So this is polynomial of degree 1, but here this is just 1 times this, so it's just a constant, right? But in general, f is some polynomial of degree n, and this polynomial actually has a special name. We call it hn of y. H is because it's pronounced the Hermite polynomial. Okay, so the list of Hermite polynomial is listed in the lecture notes, 4.1, page 121. Right, so we have solved this for the first two already, but for higher n, it becomes more and more complicated. So just now we have solved the n equal to 0 is just a constant 1, and then it's just something times linear function, and then h3 is, hang on, this is h2, there's a typo here. Yeah, so I think there's a typo missing h2 and h3. But in any case, the Hermite polynomial, you know, they take the form that looks like this. Okay? Correct, yes, energy level of the oscillator, yeah. Hermite is the describer of, yes, I think so, yes, if I remember correctly. The Hermitian that we keep saying is this Hermite. One dimensional problem that we learned, not much of a difference, right? So what you're saying is chapter 3 is one dimensional potential, and for chapter 3 we did solve a few potentials, right? Infinite square well, free particle, the delta. Chapter 4 is another potential, but we dedicate one whole chapter for this harmonic oscillator because there are like two special methods to solve this. In chapter 3, like infinite square well, these are the boring methods. I mean, these are the standard methods. So the same method is used to solve all these questions, which we did in chapter 3, right? But for harmonic oscillator, we have learned these new methods. Yeah, so if you recall, like what I say in when we started this chapter, right? When we started this chapter, an example that we mentioned was an atoms in a solid, right? So when I started this chapter, I was describing to you when does the quantum harmonic oscillator happen. So it happens here, for example, atoms in a solid, and any situation where the quantum state is close to the ground state, then is approximately also a harmonic oscillator. So it could be any situation, but one concrete example is atoms arranged in a solid, like a crystal. Yeah, so not electron orbit. But later, yeah, the next chapter will be solving the quantum mechanics in x, y, z direction. So everything that we're doing so far is only x direction, but in real life, in 3D, we got x direction, y direction, z direction. So we shall solve the Schrödinger equation in that case. Not quantum, yeah, kind of like solids, you know, that kind of thing. So I guess we will keep that for later. It's already kind of, yeah, we are a bit over time, right? So I think we should stop for today. That's it for chapter 4, the harmonic oscillator, right? Only these two methods. One pretty fun, one not so fun, one pretty standard. But that's all for today, I guess. So let me stop the recording here. And we continue next week on the 3-dimensional systems.